all the way from Microsoft Seattle.
Okay, thanks for the invitation. It's a pleasure to be here. It's been, I guess, a year and a half or almost two since my last visit here. And part of this work, last time that I was here, I was talking about random walks on expanders, on typical expanders. And that time it was joint work with my intern at that time, Allan Sly, who since became a postdoc in our group. And this is a sequel to a sequel of work with him. And also, so keep your, well, if there's, okay, he's a great guy if you get a chance to.
Competitors, not people who hire.
Yes, that's. I was about to say something, and then I thought, okay, never mind. So he's a great guy if you happen to run into him, and this is something that we've been working on for, I guess, a year, on and off until we found exactly the last nail in the coffin in an independent work, and I'll get to that later. And this will be on Ising model at criticality in 2 dimensions. Now, I'm not really sure how much, well, as to what level of detail I should go into in various topics. So I'll just try to pick it up according to your responses, but just feel free to ask questions whenever you have them, because I know that definitely there are some experts here, and I don't want to go too slow. And this is an introductory slide. Ising model so far phrased for a general finite graph G, general geometry, although our main focus in the talk, almost throughout the talk, will be the 2-dimensional square lattice. So what do we have? Suppose you start with a finite geometry. G is the graph. This is the set of vertices. We'll also refer to them as sites. And E is the set of edges, which we will also refer to as bonds sometimes, especially in context of percolation. And given this graph, we are talking about the set of possible configurations. A configuration is an assignment of plus or minus 1 values to the sites. We call those spins. A positive spin is a +1, and a negative spin is a -1, like so. So this is the hexagonal lattice. We put plus or minus spins. And the Ising model gives a measure over this finite set of configurations. And this is the measure. It's proportional. So we have a normalizer here, usually. So this is called the partition function. We have an external parameter beta. Let's ignore it for a second. And the Ising model gives the following measure to the configuration. It's proportional to e to the number of aligned bonds. So you go over all the edges in your graph, and you count a +1 if the 2 spins at the endpoint of the edge are the same, or a -1 otherwise. Okay? And beta multiplies this thing, so the larger beta is, think about beta as a non-negative, as is written here, we call this the ferromagnetic, so we prefer edges to have spins that are aligned. And the larger beta is, the more the model prefers such configurations. Okay? Of course, you can always divide by beta times the entire number of edges and then just write here the number of disagreements or and so on with a minus, and it's all the same up to the normalizer. And to those of you who are well familiar with this model, notice that I did not put inside, this is called the Hamiltonian, I did not put an additive term h times the sum of spins, called the magnetization. That's called an external field, and the reason that there is no external field here is that if there's an external field, a non-zero one, there's no phase transition in 2 dimensions, and therefore there would be no talk here. In 3 dimensions, the picture is different. And as I said, phase transition, so I didn't say what I mean by phase transition. Let's just say that in certain geometries, just like the lattice, you can extend this to infinite volume. There are several ways to do it. The easiest is to just think of limits, in which case you can ask whether there is a unique measure, there's a limit, and it's unique for the measures that satisfy this, or whether there are multiple such Gibbs measures. And there are other ways to define this this property, but this uniqueness property, which I didn't formally define and it's out of scope right now, exhibits a phase transition. So there is some critical beta up until which there's a unique Gibbs measure, and beyond that beta, there are multiple phases, and we're interested in that critical beta. And notice that so far, whatever you took from my vague explanation about this phase transition, notice that crucially this phase transition is something that describes the static system. There is no dynamics yet. So this phase transition is all about the so-called equilibrium of our later results. And finally, beta corresponds, sometimes it's called the inverse temperature. Okay, and this has to do, so the model has to do with physical motivation, of course, and perhaps a classical one is when you take a slab of iron and place it in a magnetic field, raise the magnetic field from 0 to maximum, and then bring it back down to 0. And now you're asking whether the iron retained some residual magnetization. And depending on the temperature, if the temperature is sufficiently low, then it will retain some of this magnetization. Otherwise, it won't. And there is a critical temperature at which this transition occurs. And this is what this model is here to try to attack. And so the spins correspond, well, of course, you can say that you can argue that this is a pretty simple model, but at least one of the amazing things about it, perhaps one of the reasons that there are thousands of papers on this model, is that certain parameters of the model seem to sort of be fair. So certain numbers, certain exponents are called universal exponents, and even though the model is very simple, they correspond to the actual behavior of much more complicated models, and we'll get to that a bit later. So in some sense, our work here is trying to attack one of these universal exponents.
So you'll define later more precisely what is the phase transition and what's the Gibbs measure, or you are?
No, I'll define what, no. But I'll define what I'll need for the talk. We have enough definitions as is. Yes. I certainly will define criticality. In 2 dimensions, it's much easier because all of these various definitions for criticality coincide. So it is much easier. Yeah, I could go on defining DLR conditions for infinite volume, but it would take me 15 minutes just to do that. And in this talk, we'll be interested in the Glauber dynamics. For the Ising model, which is one of the most commonly used Markov, so MC, we have MCMC, Markov chain Monte Carlo. We have a Markov chain to sample from the Gibbs distribution. So I failed to say it in the previous slides, but there is this physical motivation for studying this model. And then the most reasonable thing to ask, or the highly sought thing, is to try to sample from this model. Because as you can see in the previous slide, we have a closed form for the probability measure, but we still cannot sample efficiently because this is a huge space. Think about a square lattice that's 20 by 20. You've got 400 spins, each has 2 values. This is a huge sample space, and you cannot sample from it efficiently, or at least it's non-trivial. Okay, so you can write a closed form, but our understanding of this partition function is limited, and hence sampling is difficult. Okay, so what can we do? This is an easy recipe for sampling. We do the following. Let's assign a rate 1 exponential variable per site. We have a Poisson process with rate 1 per site, so we have a clock. And once this clock rings, this is Poisson, a mean one Poisson process. Once it rings, the site wakes up, it erases its previous value, and it writes a new value instead. Okay, and the way that it does it, so let's think about a certain site. It just needs to, the rule is you write down a new spin whose value is distributed according to the stationary distribution of the chain, which is our Gibbs distribution, the one that we aim to sample from, condition on all the other system remaining the same. So here's a small example. Let's look at the site in the middle. this plus. We want to replace it by either a plus, either keep it a plus or write a minus instead. Notice that, so recall from the previous slide, we had that the probability of a configuration is proportional to, well, there's some constant, so it's proportional to e to the number of aligned bonds. Okay? So it means that since we're not touching anything except this site in the middle, the only thing that matters is its direct connection to its neighbors, because we're keeping all the rest of the bonds exactly the same. So in order to understand what the stationary distribution of this site conditioned on everything else being fixed is, all we need to do is look at the immediate neighbors of this site. So we see 4 minuses and 2 pluses, and we can immediately calculate the probability that this should be a plus. Because when you divide, the normalizer cancels, and you can get that, I don't know, according to beta, it will be some function of beta. That let's say with probability 1/3, this would be a plus. And then with probability 1/3, you write a plus, probability 2/3, you write a minus, and then you continue. On and on. And it's easy to see that this forms an ergodic Markov chain, which is reversible with respect to the Gibbs distribution that I defined in the previous slide. And yeah, this is called the heat bath version of the Glauber dynamics. There are other versions of the dynamics, including the Metropolis one. Essentially, this means the Glauber dynamics is formally it's a family of single site chains where the rates for changing a plus to a minus have to satisfy several rules. So they have to be such that it will be reversible, they have to be bounded, it has to be translation invariant, and so on. And once you achieve these 4 simple requirements, it opens the door to several definitions, and heat bath is a natural one because of this graphical representation. Metropolis is also a natural one, and there are others.
So since you are not going to, you are caring just about the distinction between polynomial and exponential convergence of this?
Yes. Good question. How fast does it converge to equilibrium? And our results will apply to all of these chains, but let's just think about heat bath just because it's simpler.
Yeah, so I just want to say, not that it matters much, but instead of Poisson, you can just talk about picking a random site.
Yes, that's the discrete version of the dynamics. It's equivalent up to rescaling, because this Poisson one actually rescales everything by n, because everything's n times faster. But it's equivalent. This is the discrete time. The reason that I'm focusing on continuous time, this is the so-called continuous time version of the dynamics, is that there's a picture that we aim to show with respect to the second eigenvalue, to the spectral gap in this dynamics. And the picture is clearer when you look at continuous time. Otherwise, there's this extra factor of n that is sort of artificial. Okay, but so as I thought Avi asked, the crucial question is how fast does this thing converge to equilibrium? Okay, is it efficient? Will it happen in polynomial time, in exponential time? Is it rapidly mixing, and so on? So here's an example, and this example, I should be able to get to this a bit later in order to tell you what the purple dots mean. But for the experts, we are running the chain on 2 instances, one from the top position, which is all plus, one from the minus position, the bottom, all minus. And we are using a monotone coupling, which means that one is always above the other. And the red dots, or purple dots, actually symbol disagreement. So once the two chains coalesce, they sort of trap the stationary measure in between them. Now, what I said right now was a bit inaccurate, because once they do coalesce, that's a random time, and the choice of this random time then affects the stationary measure. But leaving that formality aside a bit, you can formalize it by doing coupling from the past, this Wilson-Prop method. I'll get to this a bit later. For the current purpose of just demonstrating what this looks like, we have a way of sort of saying once the purple dots disappear, then we get something that looks like the stationary distribution, roughly.
So what are the blue dots? If the purple
the blue dots, and then let's look at the final picture here. This is a plus, and blank is minus. So this is what critical easing on a 256 by 400 square lattice looks like if we force the bottom to be plus, and we force all of these guys to be minus. So we force the boundary to be what it is, and then we let the chain run. Now, just notice that it's very easy to force the boundary to be something. You just never ring the clocks of these boundary vertices, right, in your dynamics, and then you get something. Formally, this means that we're looking at the Gibbs distribution conditioned on these sites being something, and this is something I will refer to as a boundary condition. Okay, so so back to the question of this is, by the way, this is the actual dynamics running. Now a frame is every 2 to the 20 steps, so we get about 10 updates per site in what you see here, and this is at the critical temperature, at the critical beta, which I hand waved at in the first slide, which in 2 dimensions was exactly solved by Onsager in 44, or roughly in 44. And you can see that if we jump ahead a bit, the purple dots, which are, these are the dots we're aiming to eliminate. Oh, sorry. So wrong button. So as you can see, the purple dots go on and almost disappear quite quickly, which is good. I mean, it indicates perhaps a fast mixing. But then they have a tendency, once there's just a small component of them left, it can grow. So, so you see from this small component, we have something larger and larger being created.
I don't understand what these purple dots mean.
OK. So once this question is raised, let me just answer it a bit more formally. So the Ising model is what we call, I'll let this run in the meanwhile, if that's OK. The Ising model, at least here, it's a monotone system. And the way to think of it, and by a monotone system, there are several ways to see this, but think about running one chain x, where x naught, the initial position, is the all ones. And think about running another instance of the chain, y naught, whose initial position is -1, always. When you come, now we want to couple these chains so that xi will always be, let's write it like this, okay? Always be above yi. So this is a coupling of the chains where one stochastically dominates the other. Okay, and why is this possible? Well, when we come to update a site, remember that we look at its neighbors. Okay, so okay, a coupling is just a way to write down a joint distribution of the two processes such that the marginals will be the correct ones. So instead of we have one distribution over x naught. Over the xi, starting at x naught, we have this Markov chain. There's the probability distribution of x1, of x2, and so on. So this is a chain. And we have the same for the y's. Now we want to write pairs, xi, yi, such that the marginals over the x1s will be the correct ones. And in addition, we'll have this stochastic domination.
They have the same clock.
Yeah, they're running on the same system. And the way to do it is it's pretty easy. You can think of the following. What does it mean to run the global dynamics? I need 2 things per step. Let's take Avi's suggestion and run the discrete time version. It will be simpler. Continuous is just rescaling it in a sense. So in the discrete time chain, when we do a move, we select a site. So a move is comprised of 2 random variables. One is the site. Let's call it I. Okay? I is the identity of the site that we want to update. We'll use the same one for both in the coupling. The other is a unit variable u. This will be our randomness, because we said that given a site, we can look and calculate easily what the probability of this site being a plus is under the stationary distribution compared to the minus. So once we have these probabilities, we need to randomize in order to choose either a plus or a minus. This will be this U, and it will again be joined by the two processes. So we have selected this site. Let's say it was a plus in one, it was a minus in the other. It doesn't really matter because the global dynamics, once it selects a site, the first move is to erase its value. It's just a distraction. So we erase its value. And now the only thing that matters is the neighbors of this site. Now, by induction, if you will, all of these values are dominated. That is, x has larger values than y in the present configuration. Okay? It means that x has a larger chance of writing a plus here than y does. Okay? And so if this is the chance of x writing a plus, this is plus for x, and this is the chance of y writing a plus, we can always maintain this coupling and continue. And so x will always be above y, and the marginals are always the same. Now, when you start the chain, I mean, okay, the way to see why we want, there's also, it's also another triviality, but let's go through it anyway. Why do we wait until x and y coalesce? Suppose that you start another chain, z, which is distributed according to the Gibbs measure. This is what we're after. Then z at any fixed time, if we're taking a fixed time, let's say 1,000,000, then z of 1,000,000 is also the distributed according to the Gibbs stationary measure. This isn't true if this t happened to be a random time, because I could, for instance, select the random time to be the first time where z hits state, I don't know, all plus. Okay? But, and this is exactly the point that I made before, because the first time that these two couple is a random time. But let's ignore this for a second. There is a way to fix it. It's an ingenious argument by Pope and Wilson called coupling from the past. I may get to that a bit later. But for now, z, let's just assume that this random time doesn't really disturb z. Okay? In which case, at the beginning, z is between y and x, right? Because it's above the all minus and below the pluses. So it means that once they coalesce, they're sandwiching z in between them. And so the value at that point is z. This is modulo the fact that this is a random time. So to say it formally, suppose that at a fixed time, 10 to the 6, I look at the chains and they coalesce. They happen to coalesce by that time. Then we have exactly a stationary distribution, sampled exactly, not roughly according to a Markov chain becoming closer and closer. If at time 10 to the 6 they coalesce, this is the stationary Gibbs distribution, and we're happy. And the entire coupling from the past, essentially, says, let's just look at increasing times 10 to the 6, 10 to the 12, and so on, until we find a time where x and y coalesce, and then we'll sample z. Only it's a bit more complicated because you need to do it in reverse. But so now you see the purple dots were places where x was plus and y was minus. Thanks, Avi. So these were our disagreements. Once they're done, x and y coalesced. And one final thing is notice that, I mean, disagreements can grow, because if your neighborhood is not the same, it doesn't matter if you're the same, you're forgetting your value, and possibly the fact that your neighborhoods are not the same can now create a new disagreement. But once the neighborhood is the same, you will always be the same by definition. So once we've coupled, we stay coupled. OK. So here's our final picture. It looks, so we have, it's not a coincidence that I chose an all plus boundary condition below and and minus in the other three, so in all other three boundaries of our box. This has to do with, at least with the way that we thought about the proof originally. And the reason is that this nice mysterious fractal surrounding the component of pluses that touches the bottom is SLE. And we'll say something about that later. Okay. On we go. Questions so far? So as Avi asked before, and the last slide was dedicated to, we are interested in the rate of convergence of the global dynamics to equilibrium. And then you can ask yourselves, how do we measure the rate of convergence of a Markov chain to equilibrium? This is the standard notion, at least in most of the physics literature. And this is to measure convergence according to the spectrum, namely according to the spectrum of the generator of the dynamics. So let's think about, for a second, let's ignore these formulas and think about the simpler discrete time setting. In the discrete time setting of a Markov chain, you have a transition kernel of this chain, which you keep applying. Now, you can look at, this is a stochastic matrix. You can look at its spectrum. The leading eigenvalue will be 1, right? It will correspond to the trivial eigenfunction. And you can look at the second largest eigenvalue. And what we're interested is we're interested usually in the second largest in absolute value. But here it's almost a lazy chain. It will be the same. Because if it's almost lazy, then the minimal eigenvalue is about 0. It can't be around -1, and then it's roughly the same. And this quantity governs the convergence in L2 of mu. Mu's are stationary distribution, and by this I mean the L2 difference is starting at time t, starting at some state x0, is just essentially sum over all the eigenvalues except the trivial one of the eigenfunction of that eigenvalue at that initial state times the corresponding eigenvalue. So yeah, just because of the entire lights thing, I won't bother to write it again on the board. Let's just say, even if you didn't follow this quick sketch, it means that the second eigenvalue dominates this term as t becomes larger and larger because all the other ones are negligible compared to it.
Dominate just means that if it's polynomial, this gap, then
yes.
The running time will be
The
running time is polynomial in the gap.
Yeah, the reason I took some time to explain it is because it also dominates, you could say that it also dominates the L1 convergence by certain bounds. Just because if you know L2, you can bound L1, and polynomial here will mean polynomial there. It's just that I was trying to emphasize the point that it's really strongly connected to L2 in a stronger sense. You can actually see it in the formulas. And this Dirichlet formed characterization, so now we're back in the continuous time setting. In the continuous time setting, we're discussing a heat kernel, HT, which is a semigroup. And we're just looking, HT will be the probability of being, so it will be the continuous time analog of our discrete probability of being at y starting from x at time t. And it's in the form of an exponent. Well, it's all standard. The generator of this dynamics is something that I didn't put down on this slide, but it's exactly, I have to write this down. This one? This one. Okay. So LF of sigma will be just the sum of x. This is the f sigma x minus f sigma. That's it. It's a good thing because I just ran out of board. This is the rate of changing. This is a constant which denotes the rate of moving. You should interpret it as the rate of switching x in sigma. So given sigma, I want to flip site x. And then the generator will just say, this is sigma when the site is flipped minus the original value. Okay? And here, yeah, actually it should be a minus generator, f and f. This is just a way to write this is what happens if you write the bilinear form, and which is what you're.
Sorry, what is the C again?
These are the rates. These are the rates of flipping site x in sigma. And these are the ones that you can define whichever way you want in order to create either heat bath or metropolis. So you write down an explicit formula that, and you get that the rate of flipping x in a certain configuration corresponds to exactly, given its neighbors, exactly the stationary distribution of, and so on. I can write it for you later. It's really, I've wasted a lot of time so far. And it's just.
You can say 1 over n. It's not.
Okay. Yeah. So it doesn't involve n. Just it's just a function of beta in the. Yeah. Okay. But yeah, 1 over n. Another standard way of measuring convergence is looking at L1. So here we look at this is the stationary. This is the probability at time t starting from state sigma, okay? So ht sigma dot minus the stationary distribution, and the distance here is total variation, which for a finite set of states is just up to a factor of 2, the L1 distance. So we are measuring the first time t such that this L1 distance drops below epsilon. And by the way, this is due to coupling. This is a function that's monotone decreasing. It means that once our total variation distance at some time is, let's say, 1/4, at all future times it will be at most 1/4. So this is a nice object to work with. And once we've defined these two notions of measuring convergence, we can look at what the picture is believed to be for Glauber dynamics. And this is the picture that we believe happens for any graph under an appropriate definition of our, there's an implicit parameter. So if you define the implicit parameter correctly, this is the picture that we believe should occur. And it's not just we. There's a long line of papers in physics describing this picture. So we have 3 regimes. There is some critical inverse temperature beta, critical, beta C, according to which there are 3 regimes: the low temperature, the high temperature, and criticality. At low temperature, we expect the inverse gap. So remember that gap is the gap in the spectrum of the generator. So in the discrete setting, it was just 1 minus lambda 2, for instance. And T mix is the quantity measuring L1 mixing. So we expect both of these to be exponential in the surface area. Surface area here will be n to the d minus 1, okay? Because it's a d-dimensional box with side length n. And here we are talking, let's say, on the torus. At criticality, we expect there to be a power law. So we'll have n to some exponent. And in high temperatures, we expect there to be rapid mixing. So namely, the inverse gap should be uniformly bounded. And the L1 mixing time should be logarithmic, okay, in the side length n. Logarithmic in n. Oh, this is continuous time. Yes, n log n. Sorry. But now at least you can see why we wanted to discuss the continuous time case, because if you talked discrete time, then you would also have to say that the inverse gap is order n.
The main questions you ask are about polynomial versus exponential. So
in this work, yeah. But in other works, you can, yeah. In this work it will be the same. But and the second bullet here says that the L1 mixing happens abruptly. So this is called cutoff, and this is actually what I was discussing last time, which says that that the Markov chain, it starts, we're considering L1 distance. So this will be our L1 distance starting at 1, and we want to get to 0. So we're starting here. This is t, our time.
L1 distance
Yeah, L1 distance from the stationarity. So, so this is P starting from some x naught of xt in dot minus stationarity total variation. This is this axis. So we're starting from 1. And then there's a sharp transition to 0. So within a negligible period of time, we move from being, let's say, in 1 minus epsilon to being epsilon. And this is for any epsilon. This is what cutoff means. And it's extremely, so this was introduced by Diaconis and Shashahani. This was discovered by Diaconis, Shashahani, and by Aldous in the early 80s. And a good survey on it, there's a paper in 95 by Percy that discusses some of the huge challenges that exist in this area of proving cutoff, because essentially we believe that many natural Markov chains have this property, but there are very few examples of rigorous proofs for such chains. So this is one of them, where you believe that you should mix exactly at some point. So in this case, let's talk about the discrete setting. It means that you mix in time n log n, but there's also a constant like 2.3 n log n. And that's where you mix exactly. And you should wait until that constant comes in your chain, because otherwise you're in the regime where you're near 1. So it's as if you didn't run it at all. And beyond that constant, it doesn't really matter because you're already within epsilon. So you can just might as well stop. So this is what cutoff means. OK. And this picture illustrates the previous slide for the mean field setting. Mean field, so the complete graph. We have all the bonds in our graph. This is called the Curie-Weiss model. The colors aren't exactly the way they appear on my screen, but let's think of this as being red. So this is the high temperature regime. Remember that beta is the inverse temperature. So below beta critical, which was normalized here to be 1, we have a gap which is constant, 1 over 1 minus beta, and an L1 mixing time, which is something like log n. There's a constant. And notice that we know what the constant is. And this is another small observation. In the definition of the L1 mixing, there was an implicit parameter epsilon. Wait until the first t such that L1 distance drops below epsilon. Here I didn't write epsilon because given this cutoff thing, it doesn't really matter. The time to reach distance 1/4 is the same as the time of reaching distance 0.001. It's all asymptotically distinct. So there's no need to write an epsilon here. That's another way of saying what cutoff is. At criticality, we have a power law with an exponent of 1/2. And above this critical point, we have exponential mixing. OK, so just a few remarks. Here we actually showed it together with the critical window around the critical temperature of width 1 on root n. This would be fantastic to obtain in 2 dimensions, but as will the exact exponent of the critical temperature. But we'll soon see. OK, this is the picture that we aspire to show for lattices, and now we'll see what was known for the actual thing. And the reason that the complete graph is far from being the actual thing is that proving the asymptotic results here with the exact constants was delicate, but you can think about what's going on in the complete graph. You have all the possible edges between your vertices, right? So what does our Markov chain mean? We want to now, let's consider the one-dimensional chain, which measures how many pluses we have. That's called the magnetization in the graph. So suppose that this chain is now at, I don't know, 2/3 n. So we have 2/3 n pluses. What's the probability of the next move changing the 2/3 n to 2/3 n plus 1? It's exactly the probability. First, we need to choose one of the pluses, one of the minuses, because we want to change it to a plus. Okay? So choosing one of the minuses, you know exactly what the probability of that is because you know how many pluses you have. Once you choose this minus, you know exactly what its neighborhood looks like because you know how many pluses there are, and you know that you just chose the minus. So the entire chain is exactly, okay, I'm trying to say that the projection of the chain, the big Ising model, the big Glauber dynamics, onto this one-dimensional chain of the magnetization is not just the projection of a Markov chain, it's in itself a Markov chain. Okay? Now, if you start from the all plus position, for instance, then that mixing is the same as everything mixing. And for these arguments, you just need to treat first the case of starting from an arbitrary position, and second, it's a birth and death chain, it's one-dimensional, but it can be delicate to. And so we needed, I don't know, fourth moments, but it's you just do the work. It's the argument. At least you know where you're headed. And it's certainly clear that all the arguments that were required to complete this picture here do not carry to any other complicated graph, especially not for lattices.
Well, would you not expect that some similar picture holds in high dimensions, like above 4?
Okay, and the reason that we excellent question. It's the reason that one looks at the complete graph, at the Curie-Weiss model, is that it should give intuition to the behavior of high-dimensional tori. And we do believe that this picture happens for let's say, above 4 dimensions.
Above 4 dimensions, yeah.
Yeah, and also we believe that this picture also, we repeated the analysis for Potts model, and there as well we get something that should look like what we expect the truth is in high dimensions, even though that's certainly not the case in 2 dimensions.
That's a first order transition.
I know. And the picture doesn't look like this anymore. There's another critical temperature before for mixing. But yeah, so for high dimensions, we certainly expect this to be the picture.
Are there any results along these lines? Because it should be accessible by normalization methods. But.
Well, even in, I don't know, even in 2 dimensions, renormalization methods could not give the exponent at criticality.
Much harder.
Yeah, okay.
Much harder.
Yeah,
high dimensions should be mean field, right? I mean, I'm asking you because I'm not an expert. But equilibrium theory better.
So far, yeah, we didn't look at, we still don't have such results. Okay, it would be great to have them, though.
What do you mean that this should look the same in high dimension? What does it mean should look the same? Roughly looks the same. I mean, it's not a the 4-dimensional lattice or the 10-dimensional lattice is not a good expander as a clicky. So
I know, but
it
should look the same in the sense that you expect this exponent to be different. The exponent should be may be different.
You mean that there'll be
but you think that it will be the same? Oh, it would be fantastic if it would be the same.
Oh, really? Yeah. So there'll be cutoff of the same width. That's what.
So mean field theory works in equilibrium theory. Mean field theory is very accurate above 4 dimensions.
Well, it depends for what model.
For Ising.
Sort of the dream is that there are some things here that are not just, there are some exponents that really do not care if you are in 10 dimensions or in 100 dimensions, and they should stay the same. It's just like
theory, we know that.
Yeah, it's just like the true exponent here in a 2-dimensional lattice will not depend of whether it's a square lattice or whether it's a hexagonal lattice or triangular. It will always be the same.
Do you know it for an expander what the picture is?
For an expander,
yeah.
That's yeah, okay. For an expander, we know virtually nothing. So the problem with just like this called for a proprietary method, just looking at the magnetization. The only attempt we had looking at a non-amenable setting is the tree, which is already very, very difficult. And it's critical temperature, just the fact that it's there, you need to define what the n is. So the n becomes, let's say, the girth or something. So in the tree, it will be the height of the tree. And it will be either polynomial, I mean uniformly bounded or exponential in it, which means polynomial. So in the tree, just showing that it's polylogarithmic, so this power law in the parameter was this was fairly recently. This was also exactly with John Ding, who's a student of Yuval, last year, and it took, I don't know, 60 pages of recursive analysis that's very, very fit to handle trees, just because you have this nice representation of how to construct the Gibbs distribution. So on arbitrary expanders, we know nothing. Even on random deregular graphs, which are very close to trees and are your typical expanders, and usually first we prove things there before we go to arbitrary expanders, we still don't know anything about criticality. It's, that work, and there below and above criticality, it was Mossel and Sly. Okay, back to lattices. What was known on lattices? We're still in general lattices here until the last bullet. This is a long line of seminal papers which studied the high temperature regime of the chain. And the bottom line was a bounded log Sobolev constant. I didn't define what a log Sobolev constant is, as I won't need it for the talk. I'll just say that if someone remembered the Dirichlet form representation of the spectral gap, where we had this bilinear form, the Dirichlet form, in the numerator and divided by the variance, here instead of dividing by the variance, we divide by the entropy. And again, you take the infimum. This is the log Sobolev constant. Anything you say about the log Sobolev constant already implies a statement on the spectral gap. It's much harder and it's much more useful. Yeah. And notice, for instance, that in this slide, this is something that this is just to illustrate this point. The fact that T mix is log n, or in discrete time, I don't know, it's n log n, is not implied by the fact that the gap is uniformly bounded. Because, so if you had an expander graph and you're doing a random walk on it and you know that you have a bounded spectral gap, then you will mix within log n steps. Log the size of the system. But here the size of the system has 2 to the n elements, okay, and not n elements. So the fact that this is that the T mix is in L1 is log n is non-trivial, at least just by looking at the gap. It is trivial if you just look at the fact that you have contraction in your space, or, which is what reminded me of this point right now, if you have a bounded log Sobolev constant. Log Sobolev is much more powerful than the spectral gap. It's sort of, its bound is log the size of the system rather than log the size of the system. So that's exactly where you could get this log n, for instance. But this was just a comment. In 2 dimensions, these results hold all the way up to excluding the critical temperature. So for any beta, which is strictly smaller than beta c, we know that there's, in particular, a bounded inverse gap.
Is that known just for nearest neighbor or for arbitrary ferromagnetic models?
Is that, you mean, for instance, Swensen?
Nearest neighbor, so
it's known for any Glauber dynamics, for any single site. It doesn't have to be nearest neighbor. It can be
the two-dimensional statement.
Yeah, it doesn't have to be nearest neighbor. It should be. It's certainly single site, but you can look at your.
No, but I mean, do you know that all these results, these like this log n mixing,
Yes.
that they hold for arbitrary two-dimensional nearest, not nearest neighbor Ising, but I mean, are you using your nearest neighbor structure in any of this? Is my question.
So the final hammer, which is the last of these results, Martinelli-Olivieri,
Yes.
is for any single-site Glauber dynamics.
And
So
but,
you just
but in 2 dimensions.
in 2 dimensions. You're asking
Well,
what?
where's the 2 dimensions?
Oh, where does the 2 dimensions? Okay. So the last result actually it doesn't say in 2 dimensions you have this bounded inverse gap. It says whenever you have strong spatial mixing or regular complete analyticity. So this is a spatial condition.
In the equilibrium.
In the equilibrium. If the equilibrium satisfies a certain property, which we call strong spatial mixing, which in a sense, this will actually be important.
So that's almost the definition of beta C. I mean, you could make
You could make that, but in 3 dimensions, it's not clear that it is the definition of beta C. But this is this beautiful work by Martinelli Olivieri, sequence of 2 papers. You could ask, and this is something that's called strong spatial mixing, but it has nothing to do with the Glauber dynamics, this property, even though it has mixing in the name, because it's spatial mixing. You can ask how, let's say you have this box here, inside a bigger box. Okay, this is a box B. You can ask how the stationary distribution on this box would change if you modify the boundary condition. Remember that the boundary condition means I'm considering the conditional distribution given that on the event that the boundary sites are whatever they are. So this is a boundary tau. And you can ask how the projection of this conditional distribution on the box B may change if I modify tau a bit. So I'll flip this site, and I'll also flip that site. Okay? And now there's a way to measure it. A first way to measure it is to say that something has a weak spatial mixing, which means that as the distance of this box from the boundary decreases, the effect should decrease exponentially in the distance of B from the boundary. This is weak spatial mixing. A stronger notion called strong spatial mixing says that I can have my box here very close to the boundary, but I'm very far away from the support of the change, because I only modified these 2 points, y and x. And it should be exponentially decreasing in the distance from the support of the change. So if I just modify one side, it will be exponentially decreasing in this. This is strong spatial mixing. And almost strong spatial mixing is this for boxes. You could also ask the same thing for regions that aren't necessarily boxes, let's say thin rectangles. But you actually need to require it just for boxes, because this carries on even further in general models, unknown for Ising. These are all, there's a lot of literature, and everything becomes significantly more blurry when you step up from 2 to 3 dimensions. But in 2 dimensions, we know that these properties of equilibrium of the Gibbs distribution hold all the way to beta critical, excluding. And that gives us immediately the results using these.
So you need the strong spatial.
You need the strong spatial mixing.
Didn't Alistair and his student prove a general connection between the global dynamics mixing time and the spatial mixing
for general draw whites, and it was also with Martinelli. So they, okay, so yeah,
the connection between spatial and
yes, so
dynamics.
they certainly have several results on it, and. Okay, and they also studied trees, by the way. Maybe we'll say something about it a bit later. So now we're just going to talk about the square lattice, just square lattice 2 dimensions. So to summarize, in high temperature, we know that the inverse gap is uniformly bounded. And we know that there's order log n mixing for every beta smaller than beta critical. This is beta critical. It's also kind of rare that we know the exact location of the critical temperature. That's another feature of 2 dimensions. It's a model that's exactly solved. What?
You didn't define it.
I didn't define it. OK. So I can write 1 on n, right? So I can write 1 on n here.
No.
It was, yeah, I was just, yeah, so, but this,
Well, it's very simple to define. You say if beta is less than beta critical, you have spatial, exponential spatial mixing, right?
you can define it in terms of the, at least one of the features of this picture that I presented before is that, first of all, I didn't define it, but you can believe me that there's a long formal way to define phase transition in uniqueness of Gibbs distribution in the infinite volume. This gives rise to some parameter beta. Certainly, the way that the picture was formed previously defines another critical parameter, a parameter that measures a phase transition in the complexity of how long it takes the Glauber dynamics to converge to equilibrium. And what's nice is this interplay between it's the same critical temperature, and the minute that you have these properties of uniqueness and non-uniqueness of the limiting infinite volume Gibbs distributions is exactly when you turn from uniformly bounded gap to power law to exponential mixing. Okay, this was a conjecture by Paris. This is something that I mentioned before, this abrupt mixing on lattices. It was still unknown at high temperature. And this is something that we worked on with, again, with Allan, and where we showed T-mix exactly. So again, no need for epsilon because it's for any epsilon. And we know that there's abrupt mixing exactly at a given point. And here's the constant. It's 1 over lambda infinity, where lambda infinity is the spectral gap of the infinite volume dynamics, which is uniformly bounded by the results in the previous slide.
What is lambda infinity?
It's the spectral gap of the infinite volume dynamics. And actually, this specific result, we have it for any dimension. You just need to normalize the dimension correctly. But so it will be, you need to multiply it by d on 2. Yeah. Low temperature, what's known? For any beta larger than beta critical, the inverse gap and the mixing time are both exponential. Okay, so there is some constant. It's and the constant is actually was actually finally determined. I mean, this is a series of papers by Schulman, Chase, and Schulman, Martinelli and Chesi, Guadagni, Martinelli, and Schulman. So the constant is known. This is in terms of the surface tension. And we have that exactly what we expect to happen happens for any beta larger than beta critical. And the only thing that remains is to verify the power law at criticality, beta equals beta c. So is this clear so far? So we have the entire picture in 2 dimensions, except for the power law at criticality.
Well, you would also say, even in the high temperature regime, you would like to know how the lambda infinity varies as you approach beta critical, right?
Oh, we don't have the window. Yeah, we don't have the window. This would be very, very interesting. Yeah,
So
I'm clueless as to how. There is a window.
It's not just at beta c, there's a window near beta c which you'd like to know.
That's true. Yeah, this is something that, yeah, this would be fantastic to attack. Yeah. Okay.
Even physicists don't know the answer. They have qualitative things, but they don't have. It's not a soluble model, so you're not going to get. You can get estimates, but probably never an exact answer for how that behaves.
Okay, so what do we know on the critical temperature? Well, there's a polynomial lower bound. So you can ask, maybe this picture isn't true in 2 dimensions. Maybe the inverse gap is still uniformly bounded. Maybe. This was already shown by, it already followed, so this was shown by Hawley in 91. It follows from Onsager's result from 44, where he described the spin-spin correlation. So he showed that at least at high temperature, if you look at 2 spins and you look at their correlation, this correlation decays exponentially in the distance between them. At critical temperature, Onsager showed that the correlation is only polynomially decreasing between sites that are distant, one from another. So this translates to a bound that says the inverse gap is at least some polynomial. So if you do the math, you get that maybe Hawley's bound is something like n over log n. He didn't actually write down what comes out. He was just interested in showing that it's at least polynomial. So we know that it's at least polynomial, but possibly it can be exponential. I mean, you saw that from the movie at the beginning, these small blobs of purple dots sometimes can grow and grow, and it's not entirely clear that it should be polynomial, but numerical experiments, this is just a few of them, showed that there should be an exponent of about 2.17 and that it's universal. So for instance, one of these works,
What does this exponent 2.17 mean? Maybe
there's no renormalization. This is just experimental result.
I realize,
2
but
point.
what does it mean?
It means that if you have a box of n by n, then the continuous time inverse gap will be about n to the 2.17, 2.165 something. They have estimates, and they did compare these on various lattices. So at least one of these works shows square, triangular, hexagonal, all the same.
and they see the same.
Yes, and they see the same. Okay.
So this is the gap, right? This is the gap in the.
This is the gap. This is exactly what we're after. But compared to the conjecture that it should be a power law, there was no known sub-exponential upper bound. So nothing, essentially, for a long while. And the only geometries where we showed the power law for critical Ising, so we already discussed the mean field, and I did mention that we had this work on a regular tree. On a regular tree, and both of these methods are very specific to those models. And by the way, just to illustrate, I mean, in the mean field, it's a matter of studying a birth and death chain. It may be complicated, but it's, after all, just a one-dimensional chain. Here, it's a regular tree, and our upper bound was, I don't know, something like 800. Our lower bound was 2. So you can see that already for a tree, on the exponent, already for a tree, it can be very, very hard to get good estimates.
Surprising.
Okay, and yeah, I mean, we did try. I mean, I remember we tried hard to at some point to optimize until we saw that we're not even in the same ballpark as the lower bound. And then it was just, what can you do? One last thing that I ought to recall in this recap of history is the major change that happened in the last 10 years in the study of critical Ising. So there was a stream of fantastic results that followed the advent of SLE by Oded in 2000. So it started with SLE and then continued to CLE. This is the conformal loop ensemble, and tools to study conformally invariant systems. So as you can probably guess, just if I had a discussion about this with Scott when I was visiting MIT a while ago, and he insisted that it would take me at least 15 minutes to define SLE formally in order to reach a state where I can prove something about it. But as a result, I mean, the structure of this talk is such that I will hide most of what you need to rely on from SLE to a single result, which will be very clear even though I don't define SLE formally. I hope that's okay. But yeah, oh, good. That I'm always up to. But but for the time being, think of SLE as a single parameter family of random two-dimensional curves, determined by a special parameter kappa. Okay, kappa is a parameter in the driving force of the Levner evolution, of course, and of the Levner equation, and this fractal, this two-dimensional curve, was conjectured for a long time to be the line that I'm now drawing surrounding this cluster, the so-called interface of the Ising cluster. I mean, what we have here is a picture of two-dimensional Ising. We wrote purple for the pluses, and we're looking at components. And these components have an interface that looks like some kind of an interesting fractal, and it was shown in recent breakthrough results by Smirnov that these correspond to SLE with parameter 3. And one of the important roles in the analysis of critical Ising, so compared to percolation, where such results are sometimes only known for specific lattices, such as triangular lattices, here we have these results for any lattice, and the reason is that the proof goes through the counterpart of the Ising model, which is the so-called random cluster model by Fortuin-Kasteleyn, the FK model representation. Okay. Probably last slide before I get to the main result, but it is important. This is a counterpart of the Ising model. What I have here is edges that are missing or not. So percolation, bond percolation on a square lattice, but as opposed to usual bond percolation, Here where each edge is independent, here we introduce an extra constraint where we are also factoring in the number of clusters. So I'll write this down. There's only so much things that I can go through without defining them formally. So the FK random cluster model is a model on configurations that give 1 or 0 to the edges. So edges are either there or not. Okay? So omega, let's say, is in 0, 1 to the e. These are your edges. And the probability, let's call it nu, this is the FK measure, of omega is proportional to 1 minus p times the number of closed edges. These are closed. P to the number of open edges. And Q to something that's called, let's say, denoted by kappa of omega, and this is the number of components. Okay, suppose that Q, this parameter Q is 1. Then the probability that I give to this configuration is just proportional to the 1 minus p to the number of closed edges, p to the number of open edges. This is exactly bond percolation.
Closed and open means
Yes.
and non-existent.
Open is there. Open means that it's in the configuration. This is the percolation terminology. In our case, we will take, but if Q is not 1, it can, let's say, 3.5, then you introduce some kind of a dependency between the edges. And this model is an intriguing hybrid. It touches elements of Potts model if Q is integer, and electrical resistance, and of course percolation. It's a very useful tool. And we'll be interested in the so-called FK Ising model, where this Q will be chosen to be 2. So the scaling limits were first obtained for the FK Ising and then converted to Ising. And for instance, you can write down, the full ensemble of FK cluster interfaces should be SLE of 16 over 3. And these results are, so some of these results were already uploaded on the archive, others have been announced. In particular, one of the crucial elements of our proof will be Russo-Seymour-Welch type estimates for FK Ising. What does Russo-Seymour-Welch type estimate mean? It means that we're asking what the probability is of crossing from bottom to top under a certain boundary condition for FK if you have a rectangle of given aspect ratio. Okay? And we want to bound that by something. So these are the sequence of papers, Kamya and Newman, Cherkak and Smirnov, and finally Duminil, Kupin, Hongler, and Nolin. For instance, the theorem here gives such a Russo-Seymour-Welch type estimate under arbitrary boundary condition for FK. Remember that boundary condition for Ising meant fixing sites to be on the boundary to be plus or minus. For FK, there's no more sites. FK gives values to the edges. A boundary condition for FK will mean that I'm forcing certain boundary points to be connected to others. I'm introducing hard edges that are always there, which actually it forces certain sites to be in the same component. So it only matters when you come to compute this Q to the number of connected components. And as such, it affects.
But there are also always adjacent sites. Those that you connect.
You can connect this guy to anyone. Yeah, any configuration of edges on the boundary vertices. So the fully wired, there are the two extents. Just like in the Ising, you had all plus and all minus. Here you'll have the free, which is nothing. And fully wired, which means that you just connect all of them. So Okay. Finally, we get to the main result. Obviously, as the title of the talk suggested, in this work with Allan, we show that at criticality, which is this inverse temperature, 1/2 log of 1 plus root 2, the inverse gap, regardless of the boundary condition tau, regardless of what you impose on the boundary of your Ising box, satisfies that the inverse, so the inverse gap is at most n to the c for some absolute constant c. Okay, so we have polynomial inverse gap at criticality, and as a corollary, we also have a polynomial L1 mixing, because it can always be a factor of n away, log the size of the system, right?
And this is the C you expect to have is 2.2 or something, right?
Yes. Okay. So what is our C? Our C is calculated in terms of another limiting probability for this Russo-Seymour-Welch type estimate on a box with given aspect ratio, which there is another work by some of the people who were in the previous slide of calculating the conformal limit of that specifically, but it should be something, it should give a final C of maybe about 8. It's not so bad, maybe 8.1 or 8 something along those lines. And once they have so we wrote down one expression. We can also optimize our proof according to what the conformal limit really is, but it won't be much better than that. So from below, we can match, we can improve the previous lower bound, which was like n over log n or something from the work of Holly from 91 to 7 over 4. Still not the 2.17. And there are analogous results. I said in the previous slide, regardless of the boundary condition, but I said for any fixed boundary condition, it means that you fix a plus or minus or whatever. But this can easily be extended to free or periodic, which just means the torus, and also to anti-ferromagnetic, because in the bipartite setting, it's essentially the same. There's a well-known translation. Okay, so any questions about
does this lower bound follow from equilibrium exponents? I mean, there are lower bounds on that just, I think there are inequalities due to Sokol and maybe other people.
No, so okay, we tried for quite a while to use all sorts of sophisticated arguments in order to get a lower bound, and every time we just ended up with the same exponent for the lower bound. But essentially, the lower bound follows, this is variational calculus. You just want to choose, so this side is always, of course, much easier when you just use the Dirichlet form. So your test function, if this is an n by n box, it looks like n by 2n, but suppose that this is n by n. Doesn't really matter. Then what you want to choose is a small box inside, let's say of side length 3/4 n, and take the magnetization here. Sum of the sigma i's in this box, just the magnetization. And by Onsager, you know that spin-spin correlation is something like n to the minus a quarter. This is exactly your covariance. Now, I'm doing this a bit quickly. I hope that this is OK. We're trying to minimize infimum over f of this Dirichlet form over variance of f. If your function, the Dirichlet form was some complicated term, but if the function is Lipschitz, it was sum of some measure, and there were CIs, and there was a half. Let's forget what this thing was, and just remember that we have f of sigma x minus f of sigma squared. And these were sort of, so if your function is Lipschitz, it only changes by 1 in a single move, then you're averaging over something that is at most 1. So E of f is at most 1. Okay? And the variance, we now need a lower bound on the variance.
I see it already.
You see it already, because this is, you have n squared here. each guy, n squared guys, that means n to the 4th pairs times this gives you n to the 15 over 4, right? And oh, sorry, it's at most 1, but there's a rescaling again, n squared sides. So this is n squared, cancels with this, gets the n to the 7 over 4. Yeah, it's so the lower bound is simple. But actually, what's written here is a bit more delicate. I hope that it's written here. For any arbitrary boundary condition tau. Okay, so you can no longer say,
You can no longer use
yeah,
Onsager.
you can no longer use Onsager. So the way to use Onsager is to sort of say, well, I'll move to FK. I'll surround myself by a sort of a path in the dual that will disconnect me from the exterior, and this will translate me to the free setting, essentially. So you need to work a bit, but okay. But in the free case, it follows in a straightforward manner. Okay, so I said I did spend a lot of time showing this coupling argument at the beginning of the talk. And this has this, so as long as we did it, I can say a few extra words about this slide. So Mark Jerome and Alistair Sinclair in '93 had a very famous paper which showed the first efficient algorithm for sampling the Ising model. And this wasn't just on lattices, this was on general graphs. But their algorithm was adapted to the free boundary setting. So this was an ingenious, complicated algorithm to sample this distribution. Now, before I show the next bullet, just notice that the most obvious algorithm, which is just to run this Markov chain Monte Carlo, rather than to introduce a much more sophisticated Markov chain, already should be polynomial, but it was unknown that it was. And that's why Mark and Alistair moved to another Markov chain that, I mean, it takes some work, but in our theorem, we get as a corollary, as a byproduct, that you have a very efficient polynomial algorithm for sampling, and it doesn't have to be a free boundary. It can be any boundary. You just run the Glauber dynamics.
But just for the lattice.
Just for the lattice and just in 2 dimensions. Yeah. I should say that physicists, at least I was told when I was in Rome, they are mainly interested at the critical temperature. At least that's my impression. So I guess that the extra, I mean, their algorithm works for any graph. It means that it works also in 3 dimensions and 4 dimensions. But the main objective is to sample at criticality.
They sample at criticality.
Yes, they do. Yeah, I'm saying that yeah, okay.
Well, I
So-
don't understand. So what Jerome and Sinclair do, it's at criticality?
Yeah, but
It's in any graph at any temperature
Yes.
under free boundary.
Yes.
Under free boundary.
But they don't get polynomial, or do they get
No,
polynomial?
Polynomial, n to the 13 or something. They have n and m.
Run the Glauber dynamics. They run another chain.
They run another chain.
All right.
Another
So,
chain.
no, it's a modified Glauber dynamics,
Yeah,
right?
it's much more. It's not single site. It's something more,
It's
much more
non-local.
complicated.
It's more non-local.
Yeah.
Yeah, okay.
It's pretty local, right?
Yeah.
It's fairly local, but there's still some non-locality.
Um,
I understand.
Okay, now as far as perfect simulation goes, remember that I said that if you guaranteed there's this method of coupling from the past by Pope and Wilson that allows you not just to be close as much as you want to the stationary distribution, you can actually sample from it exactly. This is this abbreviation here, coupling from the past. And this was applied in 1989 by Randall and Wilson. This is a note by Dana and David that shows that you can just apply coupling from the past to the Jerome-Sinclair algorithm and get an exact simulation when the boundary conditions are free, all plus, or all minus. So now in the coupling from the past, the time guarantee, how long it takes to actually run the chain, is a function of the L1 mixing, at least in the original paper by Pope and Wilson, sorry. So since we have that the that this is polynomial, it means that in particular coupling from the past on the heat bath, Glauber dynamics, for instance, is polynomial, so we get rigorous, efficient, perfect simulation for any boundary condition. So you can write plus, minus, plus, minus, plus, plus, minus, and so on. So in 2 dimensions, and in the particular case of the 2D. Yes, so under those provisos. Okay, so so now it's the part where I'll say a few words about how we actually prove the theorem. Any questions up till now? Okay, how does one usually prove these theorems? We already discussed in the part where I defined what strong spatial mixing is. We already discussed a bit what kind of conditions are required in order for these things to hold, and this was no coincidence. The common approach for analyzing the dynamics is to control the mixing via the spatial mixing. So in order to say something about the dynamics, you first need to say something about the equilibrium, about the static Gibbs distribution. You want to characterize how fast does the correlation decay between sites. So if you show that we had this effect of a boundary, that if the effect of changing a single site in the boundary decays exponentially in the mixing, you sort of sum over these and you get what you want via a series of manipulations. However, at criticality, we know from Onsager that there is no exponential decay. There can be very long range correlations between sites, polynomial. So this destroys this approach immediately, because once you start thinking that this guy can have a polynomial effect and there are all the other guys that might also have a polynomial effect, these effects accumulate and you end up with nothing. So our approach is to sort of do something slightly different. Instead of let me erase this. Instead of analyzing how one site changing this one y in the boundary condition may affect a box that's here, we change the entire face of the box at once. And we want to measure how changing the entire face may affect this box. Now, it seems a bit strange that if you change one site, then it will have enough effect to destroy your argument. But if you change the entire face, it won't have too much of an effect to destroy your argument. But, strange things happen at criticality. And just like one site can have long-range effect, a lot of sites can, with positive probability, not have a long-range effect. And that's essentially what we use. We use the fact that the effect of changing an entire face can die out within a reasonable, let's say, linear distance.
Change by how do you change it?
You replace it by something arbitrarily different. Arbitrary, not adversarially. So you take the entire set of values, and now you write down something, whatever you want, and you compare the worst case difference between the two. And you want to say that with some probability, it will die out before affecting your part of the box here. Okay, and
a little counterintuitive, right? Because so when you say you change it, you mean you have to change everything, or so I don't quite understand. I mean, I could just change one site and I would still have the problem that you mentioned, right? So why is it that when you change a block or
because we do want to change, in the previous applications also, we are always interested in changing entire faces.
I understand that. Yes.
But and the way to achieve it was sort of just count the effect of one and just take the sum.
That's not a good idea, of course.
Yeah, not here. It was a good idea there.
Okay.
But here we need some kind of method to help us analyze what happens when we do it at once.
Okay.
Which is where we use the FK model.
Okay.
Okay. Yes?
What is the probability that you mentioned over?
That you what?
So you changed one face
I'll say it precisely in a slide. This strong, our spatial mixing result. I'll state it precisely. This is by the way, this is a comment that I'm not sure, maybe I should have inserted it before. This says that actually, if you have an m by n box, this is what we prove. We prove something slightly stronger. If you have an m by n box, then the inverse gap is at most n to the c, regardless of m. So you can have a box whose side length, well, the proportions are n by e to the e to the e to the e to the n, and still your inverse gap will be the same n to the c. Okay, it only depends on the shorter side length, which is also, so you see, working in continuous time reveals, is useful for revealing several, so here, because in discrete time you would always pay the volume. Yeah, you can.
We erase it later because it's a normalizing factor. But
Yeah, okay, yeah, that's true. Well, it's all the same. It's all the same. Okay, so it only depends on the shorter side length. And now we can go back to our strong spatial mixing result. So you asked what the statement really is. Let me.
But I mean, to answer Amir without the formulas, you are looking at the stationary distribution. That's what the probability is over. Stationary distribution given. And
Yes, we're trying to. Oh, yeah. I'm sorry. So I thought that you asked something more specific. Yeah, we want to understand what the different. Just as before, we have. So in the previous setting, when we defined strong spatial mixing, we had some kind of box here. Okay, you had some kind of a boundary condition tau, and you were looking at mu of B, okay, given this boundary condition tau. The projection of the conditional distribution under the boundary condition onto the box B. And now you compare this to what happens if you look at tau primed, which is exactly the same, except it has this spin flipped. This is a standard thing to argue. And you want to argue that that let's say mu tau B minus mu tau primed B in total variation is small.
Yeah, that's just a number.
This is an arbitrary change of the boundary.
Yes, you say that the equilibrium measure, Gibbs measure, mu, satisfies this strong spatial mixing in space, if for any box B, this thing, okay, and for any boundary condition tau, and for any y, this thing decays exponentially in the distance between B and the support of the change. This is a statement that is deterministic. There is no probability there. You can think of mu as a function and just say that this is a property of the function.
And the statement that you said before, that when you go linearly far after you do an arbitrary change of the boundary.
This is something that I will. This is what I thought you asked before. So this is something that I'm going to formalize now. Okay. So now in this theorem that looks a bit more complicated than it really is, okay, we have this this big box lambda, and we're considering as the upper part of lambda, which is lambda top. Okay, this is this lambda t. Okay, so this is the entire box that we have, and we are looking at the top, which is lambda t. And eventually we'll want to say something about the projection of mu onto lambda. Exactly like we discussed right now, the projection of mu onto B. Sigma is, this is a standard notation. Sigma is the Ising configuration. It's just the value of sigma on the top triangle. And we want to say something about the total variation distance. So the statement of the theorem is, if you have your box lambda in two boundary conditions that only differ on the bottom. Okay? So here, and here, they are exactly the same, but the bottom face can be arbitrarily different, adversarially different. then then we can bound the total variation distance between the two in the following way. Let's write it in other words. Okay. Let's suppose that this line is at the 1/3 line. This is n by n, and this line is at 1/3 n, a linear distance. Then we can say that the total variation between the two is bounded away from 1. It's a constant. Forget about this. This statement is actually, it's useful because if you want to show the theorem that I just said, the more general one on an n by m box, you have to have something that also controls, that also decays exponentially with the distance of this line. But for now, we really have no time to get into those details. So let's just think of this as a constant bounded away from 1.
Then you have to patch them together.
Yes, yes. You patch them together, and you use some kind of a domain Markov property because we're working in FK in order to just accumulate these into independent errors. Then you get something exponentially small in the distance. But it's like independent trials of every time if you didn't reach beyond a certain level, then the effect of this changed boundary dies out. So, okay. Yeah, okay. Thank you. So with this spatial mixing at hand, we have, this is a classical proposition. You can find it in Martinelli 97. It goes back at least until Holly. It's called a block dynamic approach rather than the single site dynamics. It's really tailored to the Glauber dynamics. And this is a standard practice in the analysis of the Glauber dynamics. We have a very complicated argument here, relatively, at least compared to the late hour and the fact that everyone is hungry. So let's just ignore everything here and just notice that the two terms in the numerator and denominator are the same, except that we have this capital N here. Okay? And now I can say 2 lines about what this block dynamics is. This is a way to short circuit your dynamics, to do a shortcut.
It's like a zigzag. It's the same. You have, right? I mean, you your graph from components.
Yeah. Yes. It's very similar. Yes. So so you think of the following: instead of just taking one site at a time, let's partition the graph into blocks. And now the move is exactly before. What did we do in the single site Glauber dynamics? We picked a site, we erased its value, and then we wrote a new value of the stationary distribution condition on the rest, right? Now we do exactly the same, just we do it for an entire block. So we have a block, we erase it. So, we have our graph. We partition it into blocks. They can be overlapping. And the operation is take this block, erase its value, and now it has an interface with the remaining graph. So this interface induces a probability measure on this block, and you just write an instant version of the entire block from scratch, replacing the previous contents. And then you do it again. So each block has a Poisson clock, and it runs on its own, just like the site had a Poisson clock. And now I can shut down this slide.
Is your X a block now, or what? The sigma X.
Oh, how did I turn it on? Okay, good. Okay, okay, so first of all, the dynamics is clear, right? So we just update blocks independently. The proposition relates, so this is a Markov chain. It can be shown that it is reversible with respect to the same Gibbs distribution. And as a Markov chain, it also has a spectral gap. The proposition relates the inverse gap of the original single site dynamics to the inverse gap of the block dynamics. So what do we have here? Our inverse gap is at most something that incorporates nx, the number of times we covered each single site in the blocks, because they have overlap. Okay? So you should think of it as...
They don't have overlap if it's a partition, then it's
yeah,
one.
then it's just one. Right, and then this entire thing vanishes. But it will be useful to have an overlap. But if it's one, then this thing cancels, and then you bound your dynamics by the inverse gap of the Glauber dynamics times the maximum of the individual single-side dynamics on the different blocks. Yeah, it is a... It's exactly like a... Yeah, I never thought about it.
It's exactly like in Randall and Martin, where they do it in the language of Markov chain. The only difference here is that in Zigzag and Randall Martin is that you argue about the graph itself, and the partitions are, you partition the graph, and you're just exactly the same. Here you're talking about the exponential size Markov chain running on your graph, and you partition it rather than...
Right.
So you
yeah,
partition the graph, but you are arguing about...
yeah,
the Markov chain...
You're partitioning another representation of your...
exactly.
Yes.
Yeah. But the statement is exactly the same. So it's,
okay.
And they have Martin and Randall have a version with covering as opposed to partition also.
Okay, so here again I want to ignore the formulas for a second and think about what happens if I take my big rectangle and partition it into two overlapping boxes, okay, lambda 1 and lambda 2. Let's think about the block dynamics, okay, because you can think that in the previous proposition, you translate the entire thing into a product of the single-side block dynamics on smaller side rectangles. There you can use induction. Suppose we don't care about losing constants. The actual proof is a bit more complicated because you do care about losing constants, but suppose you don't. So you just reduce to smaller sized blocks by a linear fraction. Let's say that this thing is linearly large, and that's why it's important to have an overlap. Well, okay. Not just, but yeah, okay, it's a constant, yeah, okay. But and the main term to bound is the gap of the dynamics itself. What does the dynamics itself do? Well, you take lambda 1 at some point and update it at once. And then you choose lambda 2 and update it, and vice versa. Sometimes you'll update one of these guys twice in a row, and so on. Our strong spatial mixing argument, let me just pick at, okay. Our strong spatial mixing argument says that I have, in 3 minutes I can give you a better sense of where this is going. We take this big block, lambda, and divide it into 2. This will be lambda 1, I hope, yes, and this will be lambda 2. Okay? What does the gap of the block dynamics look like? Suppose we first update lambda 1. Okay? Now, here we have the way to control the block dynamics is, as usual, I mean, one easy way to do it, run 2 chains, just like we did at the beginning. X naught will start from the all plus, and y naught will start from the all minus. So we have 2 chains coupled exactly as we showed at the beginning of the talk, monotone coupling. And we want to wait and see when these 2 will coalesce. And once they coalesce, I mean, the limit of the time it takes them to coalesce, this is exactly your spectral gap. It can be seen. So it's sort of it governs the difference once you take the roots away. So we're asking how long it will take these all plus and all minuses to coalesce. Now we start, suppose that the first move is to update lambda 1. So it's taking this guy and updating it. And we're updating it in both chains together. Now, here's how the theorem, the spatial theorem, makes sense. Look at the boundary of lambda 1. We had an initial boundary tau. It dictates the boundary here on lambda 1. However, the bottom boundary on lambda 1 is dictated by the value of x on lambda 2. This may be different between x and y, because x and y are different. I mean, for instance, they start the inverse one of the other. So the bottom boundary differs, but the other three boundaries are the same. Now, our spatial mixing result tells us that if we have three boundaries that are the same and one that's different, then with fixed probability, the total, I mean, this is another way of formulating the statement on total variation distance using maximal coupling. With fixed probability, we can couple lambda 1 top, this part, between x and y. Because x and y are now updating both the top rectangle. They have only a difference in the bottom boundary. So we can couple this guy. Now, if the next move will choose to update lambda 2, it has exactly the same boundary because the top is the same, which means that in the next move, we'll have exactly, the coupling can choose to have exactly the same values of x and y, and altogether they are identical. So we're done. So the spatial mixing statement tells us that this block dynamics is uniformly, the gap of it is uniformly bounded. And being a little more delicate, you can do this. This is this trick from the Kawasaki paper by H.T. Yao to not just choose one of these, but to average over various choices of blocks in order to get to eliminate some dependency in constants. But it works. You can. The rest is it's a bit technical, but it works. Okay, so we're done, and hopefully by now I convinced you that if you have this strong spatial mixing theorem, then you can plug it in the analysis and get a polynomial upper bound, because each time you recurse into, let's say, a constant fraction of what you had before, and you pay a constant. So you do it log n times, constant to the log n gives you a power. And now the question is, why should this strong spatial mixing result be true? Why did we even get to think about it in the first place?
That's a little strange because you're critical, right?
Yes. Yeah, I mean, it's OK, so at first we said, OK, what happens, let's say, if you start from one box and you're running, so this is the first application of the recursion. Let's say there's free boundary. So you are free, free, free. And in the bottom, you have a different boundary between the two chains. So one is plus and one is minus. OK? Then we know that, let's look at the plus. OK? Let's look at the plus chain and look at its component of plus that's touching the bottom. We know by things that I did not have time to define that this looks like SLE, the component that's touching the bottom. And even though I didn't define it, think of a two-dimensional Brownian motion. So Brownian motion, if you select any tube, it has positive probability of not exiting this tube. You need to choose. So here, no matter where I choose a line that's linearly high, it can be at 1/3, at 1/4, at 1/10, with some positive probability, this Brownian motion will not exceed this line. So it means that with positive probability, the plus component of the plus instance, the x, will not exceed this line, but it majorizes the minus component. So it means that the minus component also does not reach beyond this level, which means that if I expose them gradually, one by one, sort of from the bottom, I can, at some point, they will be the same, and I could sort of couple them to be identical above it. So I can couple the plus and the minus here. So the strong spatial, in other words, with positive probability, this entire top rectangle will be identical, which means that the projection of the stationary measure on it is strictly smaller than, I mean, you see where the proof goes. So this is what would happen if we had free, 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 and a difference.
You're talking here about the
Ising. Equilibrium result, there's no mixing. I'm now talking about whether what's the total variation distance on this top rectangle if I have free, free, free.
Bounding it by the probability of x
of the component reaching this line. Yes, exactly.
And this follows from just the fact that this is SLE free.
Yeah, it follows that it's subcritical SLE, that it's not space filling, that it's so yes, exactly. Just from the fact that it's especially, there are several kinds of SLE depending on the parameter kappa, and for this regime, it's a simple curve that will not exceed this line with positive probability. That's all you need. However, let me just say why things, I mean, this is something that this is what started our approach, but of course it fails miserably. And the reason that it fails miserably is that there's a small detail in the proposition on the block dynamics, maximum over phi. This isn't just, when you do this reduction to you recurse to what happens in the single site dynamics on smaller blocks, you have to take the worst possible boundary of these blocks. And this is an imperative step in the proof. Worst possible boundary, because in a sense, when you recurse, you're sort of saying, okay, whatever I did right now in the block, I have a certain value of this block. This determines the boundary condition on the other block. Let me run the other block, and so on.
And you cannot take a typical one?
No. You have to take a worst.
This is a Russo-Simon.
What?
This is a Russo-Simon wave sim,
No, not yet. This was just the block dynamics version. It told you that when you do the recursion, you have to take the worst possible. So in our proof here, when we said, okay, we want to say what the total variation distance is between two instances that run here, we should assume the worst possible boundary conditions here. Because after we apply our method 10 times, we will no longer be in the nice regime where this is the exterior, the large rectangle. We'll be in a half of a half of a half of a half of a block, somewhere deep inside, and it will have arbitrary boundary. And on arbitrary boundary, there is nothing known. There are no SLE results known. There are, I mean, this is a breakthrough, amazing result. Just, I mean, right now, there are just a set of specific boundary results, boundary conditions where these SLE results are known to hold. The Dubruchin region, I mean, you have free plus, or so on. But for an arbitrary boundary condition, it's very complicated. So the method fails. So what do? Here we want to move to FK. So the idea is, let's look at the bottom line. We want to move from Ising to FK. So there is an equivalent representation of the Ising model using the random cluster. And then we want to move from FK back to Ising. Okay? And in the FK world, we are able to handle arbitrary boundary and get the analog of this non-crossing of the clusters. There's an obstacle in this way which says that moving from Ising to FK and back is conditioned on some event which may have exponentially small probability. Okay, we have 2 minutes. Since this is a main part of the proof, and I did go through the trouble of explaining to you what FK is, I can just say what I mean here. We have 10 minutes? Oh, that's even better. On the left here, we have an Ising configuration, blue and red for the spins. There is a way to generate from Ising an FK configuration and go back. Let's focus. This is a well-known coupling method. This is the Edwards-Sokal coupling. And let's just think of the following. You know what? Maybe if we have 10 minutes, then I can do something easy that will give us a sense of achievement. Remember that in the FK configuration, we had omega giving 0 and 1 values to the edges, and the probability was proportional to 1 minus p number of closed edges, p number of open edges, and q, which I'm writing now as 2, times the number of components. This is components. The Edwards-Sokal coupling tells us that if I have an FK configuration, okay, a way to generate Ising is the following. Generate FK, you get a configuration, just like here. You see, this is a cluster. The reds formulate a cluster, the blues here are a cluster, this is a cluster, this is a connected cluster. Okay, connected components of this configuration. Now take every component and flip a fair coin for its spin independently. The entire component gets either a plus or a minus. This gives you an Ising. And why? A way to see it is just to say, what is the probability of getting a certain configuration sigma? Oh, I forgot to say. We need to choose. This is for a specific choice of P. This is crucial. I mean, Ising with parameter beta corresponds to P with parameter e to the minus 1 minus e to the minus 2 beta. Okay, why does this work? Well, suppose that we want to look at the probability of a certain state sigma. Ising. So what needs to happen in order to randomize it according to FK? Well, first of all, we want to never get edges that are between a plus and a minus in sigma. Because if the FK has an edge between one of these, it will, by definition of this coupling, give the entire component the same spin, and we can never hope to have different spins in the two of them. So these are forbidden edges. We don't want to touch those. Okay, so we have like something like 1 minus p number times the number of disagreements of sigma. First of all, we have to omit these edges. As far as the other ones are concerned, we have 1 minus p for each one that's not there, p for each one that's there, times the number of clusters. But for every such configuration, we then, in order to generate sigma, we need to choose each cluster to have exactly the spin that we want. So the probability is 2 to the minus number of clusters. This cancels with this 2 to the number of clusters and leaves only 1 minus p to the closed, p to the open, over all remaining edges. You sum over all the configurations, so it vanishes. So you're just left with this. What is this? 1 minus p to the number of disagreements. This is exactly e to the minus 2 times number of disagreements. And now if you multiply this by there's a normalizing constant of the FK. Now you multiply this by another normalizing constant, e to the beta times the number of edges, and you get exactly the Ising. Okay, so this shows you how to move from FK to Ising. But now we have an arbitrary boundary, which makes things much more complicated. This was all if you have free boundary. And the thing to observe is that we can run FK with a boundary condition in the following way. Suppose we wanted to have exactly these boundaries. Blues, reds, blues, reds. This is part of the boundary.
So it just makes the connection.
We force the connection of the FK, exactly like Avi said. First of all of the blues have to be pairwise connected. So we do it. That's why I wrote them as blue and red, wherever they are. And now we run the FK as usual, and we hope that we don't get a path that connects the blue to the red. Because if we do, we are doomed, and there's no way to recover the Ising. But condition on the event that there is no path between a red and a blue, then we know that with probability a quarter, if we run the usual Edwards-Sokal coupling, this cluster will get blue and this cluster will get red, and we'll get a legal Ising configuration. So I'm trying to say that the Ising induces a wiring on FK, and condition on the event that there's no bad path connecting the two types of boundary vertices, we can go back to Ising. So this is an event AXI that depends on the boundary. And notice that this event can be extremely rare, because if you have red, blue, then the probability of a path is very large. In each of them, it can definitely be exponentially small, this event. So you need to work condition on an exponentially small event, which makes things delicate, but still doable. At least we have a framework. And here, in the world of FK, we apply this Russo-Seymour-Welch type estimate. So we say you have three boundaries that have various conditions but are the same in our two chains. now it's no, sorry, it's not a matter of change, it's two instances, yeah? We're talking about equilibrium now. We have two sets of boundary conditions that are the same everywhere except at the bottom. And we want to say that the effect of the bottom doesn't rise beyond some level. So modulo the fact that we have this event that we need to condition on, which makes things more complicated, you can, I hope you can trust me when I say that you can majorize both these conditional measures with the fully wired FK measure, because, and the majorization works by FKG. This model has FKG, and you're conditioning on a decreasing event. These are details. So let's, for the sake of the discussion, let's forget that we're conditioning on this event A. Then we have two sets of boundaries that are the same everywhere except at the bottom, and both are measurized by the all plus measure. So everything is wired. Now you expose the component that touches the bottom, and the all plus, the fully wired one has a positive probability of not exceeding this line by Russo-Simmer-Welch. But if it does not exceed this line, then in the dual you have a blocking path. A blocking path in the dual in the fully wired one that majorizes the other two, so it has to be there as well. So when you expose the rest of the edges, they can be identical with positive probability. So with positive probability, both these measures are identical above this line. And now you need to sort of worry about this exceptional event A and see that everything remains the same, and you can still go back to Ising. But at least you can see, I hope, where this comes from. So we move to FK, apply Russo-Simmer-Welch under the fully wired boundary condition, which is the worst. You see, because, I mean, in the FK, if you have more wires, you increase the chances it's monotone. There's a monotonicity in boundary conditions. You give it a push towards climbing from bottom to top. And yet, remarkably, this is why this Russo-Simmer-Welch type estimate is so surprising. Even if you put all the wires around yourself, there is a positive probability that you will not make it from the bottom to the top. Here, in our case, this is our top. And we're saying we put a fully wired condition here, and still we will not make it from here to here. And since we're not making it from here to here, there has to be a blocking path somewhere here, and so on.
This is not an SLE result.
This was proved. This is these three papers that I cited, and they use the SLE machinery in order to prove it. And again, so again, it's first proved on FK, and then you can infer results on Ising. And there is, I mean, given the aspect ratio here, or the conformal modulo, there is a limiting probability for the crossing, and it's a conformal, I mean, there's a conformal limit. It will not depend on the lattice. And so the machinery that they use to prove such statements is drawn from the studies from Smirnov's papers, actually. So it relies on the Smirnov and Shelcock's previous paper from last year. Yeah. Okay. So the only thing that remains. So these are two extremely challenging questions. One is to get the precise exponent. I mean, we get something that's logarithmic in this limiting conformal parameter of crossing probabilities in the FK, which is a rough upper bound of maybe 8 or 9 or so. And there's the question of just what this thing really is. And 3 dimensions where we have no SLE, no Russo-Simmer-Welch type estimate. I mean, many of these things will just not be true, many of these correlations, and we are just lost.
But isn't it true that the global dynamics should at least, be faster in 3 dimensions than in 2, even at criticality at any
faster at
converge faster. I mean, it's more again. It's a better expander of 3-dimensional.
Yeah, I don't know. There are there are far more trivial statements that it should also be true, for instance, that if you increase the interaction strength somewhere along edges, then you should only mix faster. It should be true that that free boundary.
No, that's not a uniform. I mean, if you increase it somewhere and you don't, maybe you create. You know,
Oh.
but I don't think it's an obvious. And
Okay, it
this
should.
is something that you do uniformly. It's just.
I guess.
let's say-
What if you add external field to every point and you sort of
same
push?
or the
Yes, the same. This is also unknown. If you just increase the, it's there are several of these conjectures that seem obvious, but they're unapproachable so far. Presumably, any sort of strength that you put on the model. So, for instance, all plus, I didn't say anything about it, but in 2 dimensions, all plus boundary condition, it's not mixing exponentially slow above the critical the critical beta. It's sub-exponential. There's a remarkable breakthrough by Martinelli and Toninelli that showed that it's e to the L to the epsilon, where L is the side length. It's conjectured to be something like L squared. So that's if you put all plus. So presumably any sort of external interference that you put should make it faster, but it's not, it's unknown. Yeah. Okay, that's it.
And more questions too.
What about dimers?
Oh, I can.
That's a simpler question, right?
Yes, David Wilson will know more about that than me, but yeah, there are.
So you know that you can, there are various moves that you can, I guess, this goes back to Jerem and Sinclair and Luby and Randall, I don't know who's involved in it, but you know that you can equilibrate, and it's critical in 2 dimensions, so for a square lattice, for example. So you equilibrate in some polynomial time, I believe.
Mm-hmm.
I mean, it's very close to Ising, as you may know, because Ising is a special form of dimers, in fact.
Yeah, so we didn't really, we didn't consider hardly any other model than the, except for the ones that are here.
Mm-hmm.
And so the only things that we did think about as obvious extensions are Swenson-Wang seems very relevant just because we're walking through FK anyway, and it's kind of,
Yes,
but
can you say anything about that?
not yet.
No,
I mean, it has to be faster. Swenson-Wang is when you flip entire clusters at the same time. And in mean field, it's known to be slightly faster. Yeah.
Is
So,
there a theorem that tells you that, is there a lower bound?
that says that it's a, I don't know. Yeah, good question. Bless you. And also another thing I should say is that if you prove Russo-Seymour-Welsh for, bless you, for random cluster FK, but not FK Ising, for a different Q, for Q equals 3, for Q equals 4, you can just plug it in our machinery and you'll get the polynomial upper bound for Potts model at criticality in 2 dimensions, and everything should work still, at least in 2 dimensions, right?
So it all depends upon this Russo-Seymour-Welsh with these general boundary conditions.
Yes. Once you go through the machinery of the recursion and you consider this event and you do everything carefully, it all just boils down to controlling Russo-Seymour-Welsh on there. Yeah. So the machinery should work, but nothing is known for Q equals 3.
Q equals 2, right?
Yes. So far there are no results on Q equals 3.
And Q equals 4 or 5 would be false.
Right. At least, yeah, presumably.
Yeah.
Yes. Yes.
All right, thanks.
Okay.